welcome to my presentation. I'm Gabriela and I'm a PhD student at Johannes Kepler University Linz. I will present to you a challenge case proposed to the SPLC 2021 by David, Wesley, Lukas, Paul, Alexander, and me. Managing systems evolving in space and time. 4 challenges for maintenance, evolution, and composition of variants. Software companies have to tailor and maintain variants of software systems coexisting simultaneously to serve different customers and new requirements. This results in many system variants that have to be maintained and evolved in parallel. Thus, over the system life cycle, the introduction of new features in existing variants, also known evolution in space, can be required. Further features can be subject to failures or unwanted behaviors, and bug fixes have to be done introducing new revisions of features, which is referred to as evolution in time. Furthermore, the evolution in time results in variant revisions, which are sequential versions of a variant, containing different artifacts for the same configuration. That is a set of features. Variants of a system are composed of variable sets related to different features that realize the variability of system. And the system variants reflect different configurations and have been described as variability in space. The variability in time, on the other hand, results from the need of modifying variants due to enhancements, for example, to address new customer requirements or changes to the environment, such as alternative hardware or the optimization of non-functional properties. The system evolution in space and time can be tracked by applying feature location techniques, which goal is to identify which artifacts of the variants of a system belong to which features. Thus, the feature location is an essential test to support software maintenance evolution. Furthermore, it is the first and one of the most essential tests of the re-engineering process to migrate the family of existing system variants into an SPL. Despite feature location and software product lines cover the space dimension, they do not address the time dimension. Software product lines by themselves do not provide proper management of evolution time, and engineers have to adopt additional mechanisms and tools. Some pieces of work point out the need for a software product line to have a portfolio to reflect potential versions of a feature. That is, the feature revisions that coexist, which can be used for creating different variants. Existing feature location techniques can locate features of a system or a set of features, but only at one point in time. Although there are some feature location techniques considering the space dimension, they have limitations. For example, coarse levels of granularity, generally at the method level, and are not yield good results when applied to single systems. Still, regarding the time dimension, there is only one feature revision location presented by Michelon et al. 2020 that is able to retrieve traces of feature revisions, but it is still an approach that is in the early stages of development with suboptimal results and limitations, for example, in terms of the number of feature revisions that can be located. Yet, there are few benchmarks available that can be used to apply feature or feature revision location to C preprocessor-based systems. A benchmark for C software systems would ease the proposal and evaluation of feature revision location techniques, because C is widely used for realizing software product lines with preprocessor directives. We thus stress the need of introducing new or improving existing feature or feature revision location techniques by proposing 4 challenges to motivate researchers and tool developers to optimize and address the limitations of existing techniques, and to develop more efficient mechanisms for managing systems evolving in space and time. We thus now present our first challenge, feature location at one point in time. With this challenge, we aim to motivate researchers and tool developers to evaluate existing or new feature location techniques based on systems developed in C or C++ using our benchmark enabling the study's reproducibility and comparison. We also want to motivate the development of approaches for automation of the use of features for composing new configurations. We thus present our second challenge: composition of new product configurations with a set of features. With this challenge, we evaluate if the proposed feature location approach for C or C++ systems can be used to compose new configurations with the traces retrieved to simplify and accelerate the composition of not yet existent variants of a system. We present the third challenge to motivate researchers and tool developers to improve our feature revision location technique or propose new ones overcoming current limitations. The third challenge is a feature revision location at multiple points in time. By raising initial solutions for systematic reuse in software systems evolving in space and time to the level of features, developers and engineers can benefit not only when propagate bug fixes and refactoring, but also when creating new configurations with different behaviors of the same feature. Thus, our fourth challenge is composition of new product configurations with a set of feature revisions. With this challenge, we expect solutions that can automate the reuse of existing feature revisions of a system in order to compose different configurations, with different implementations of features at different points in time. Thus, our contributions are a benchmark which contains a ground truth dataset with variants from 3 C open source systems evolving in space and time with their respective configurations at one point and multiple points in time, and also 2 utilities to evaluate the efficiency of feature or the feature revision location techniques proposed that is able to compute automatically metrics for evaluating them, and a ground truth extractor generator tool. Both you can have access by scanning the QR code. The dataset of our benchmark is extracted from 3 subject systems which have been used in previous studies already and are managed in Git repositories. The libSSH system is a multi-platform C library implementing this SSH-v2 protocol on the client and the server side, and this project was initiated in 2005 and now has around 5,000 commits in the master branch. The Michelon system is a variant-rich open-source embedded firmware for 3D printers created in 2011 and with currently around 15,000 commits. The ERC system is an internet relay chat client for Linux with around 6,000 commits since 1999. For the challenges with variants with features, the scenarios for evaluating solutions for challenge 1 are from variants containing a set of features from one release, that is, the state of the system after the last commit of a release in the repository. We designed 30 scenarios of each system with a specific number of variants, where scenarios 1 up 10 have 1 to 10 input configurations, and scenario 11 has 100, scenario 12 has 200, and scenario 13 has 300 input configurations. This is about 26 to 104 features. For challenge 2, we make available 50 new configurations that do not exist in any of the scenarios to evaluate the solutions. For the variants with feature revisions, we used scenarios for evaluating the challenge 3, containing 400 points in time from the first 400 Git commits. With this, we designed 9 scenarios for each system according to a specific number of Git commits by varying the number of variants for each system. For all 3 systems, we present scenarios consisting of locating feature revisions from 1 point in time to up 400 points in time. And then the scenarios vary from 1 to 683 variants, 142 features, and 0 to 536 feature revisions. For challenge 4, we make available also 1 new configuration for each point in time, where solution, proponents can combine different feature revisions for all the scenarios presented in this work. Furthermore, we make available an additional scenario for the LibSSH system with a set of 6,730 variants, resulting in 6,596 feature revisions from 103 features, thereby covering the entire evolution of the master branch. Regarding the format of the proposed solutions, the ground truth is composed of a set of variants, and thus the results should be variance artifacts composed with the mappings of each feature or feature revision of configuration. This allows for multiple valid traces. Additionally, we expect the result files from the matrix computed, which we will explain next. For the matrix, we use two levels of granularity due to the granularity of the ground truth extraction. The variants can be obtained from lines that have been added, removed, changed in source code, or in binary and text files from Git commits. Therefore, the matrix can be computed at the granularity of file and line level. The file level comparison checks if two complete files, ground truth and retrieved, match their content, while the line level analysis compares every line of source code of two files, ground truth and retrieved. The correctness must be computed based on the comparison between the ground truth variants with corresponding retrieved ones obtained after performing the feature revision location. The precision is the relation of the true positives, that is the correctly retrieved files, which entire content matches, and false positives, that is the files that their entire content does not match. At the line level, true positives are lines of source code that match related to the lines of source code retrieved by the technique that does not exist in the ground truth variants. The recall is the relation of the false negatives, that is the files or lines of source code that exist in the ground truth variant but were not retrieved by the technique. The F-score is the harmonic average of precision and the recall. And to evaluate the scalability of the feature or the feature revision location techniques, we expect proponents to compute runtime and memory consumption, reporting the specification of the infrastructure used to run the proposed solutions. These metrics can help to compare and improve techniques regarding the time complexity and space complexity. That is, how much time a technique takes to locate features or feature revisions for each variant, and how much memory is necessary to locate features and their revisions for a specific number of variants. The ground truth approach, it first needs the set of features to then identify the feature revisions and mine ground truth variants. And as we don't have always the set of features known, we defined an automated approach for identifying features. But the approach enables that the features can be set manually, and then the users can follow with the next process of mining feature revisions. In case of identifying features, the approach looks for all the if-defs in the source code files and also the defines. When a feature is inside a define within the source code, we do not consider this annotated feature as part of the features, as they are internal features. We just consider part of the features that can be set externally by the user. So in this example, we show the features Advanced, Base, and AVR 80MB644p. The base feature is the feature that we use to characterize the core of the system, or the other code that does not belong to any annotated feature. The mining feature revision process then consists of analyzing for each line that changed which feature is the feature that belongs to the changed block of code. We always analyze the feature revision belonging to the changed block of code for the closest ones, but we also have to consider for the configuration of preprocessing a variant for a specific changed code all the features that implies in activating this changed code. So for example, in this slide, if the changed line is the line 11, we would assign to this line the feature revision AVR 80 mega 640p 44p, but we also need to have in the configuration the feature that activates motherboard, because this code will only be executed if the motherboard is equals 1. So we have to look up the files and create constraints to be able to know which features have to be in a configuration to have this changed block of code. And for this, we also use a solver to get basic arithmetic operations and comparisons of numeric values in the range of integer or double despite basic logic operations and Boolean values. In this example, if the line 5 changes, the feature revision assigned to this change would be advanced. And for this example, if a line of the block, if not def configuration is changed, the change is assigned to the base feature as the block of code contains the outermost condition, if not def configuration. And it means that configuration is also an internal feature and we don't have an outermost feature that influences on this. And in this case, if not def means that this block of code will be executed if this feature is not selected. So we assign this change to this block for feature base. So with this example, we would have feature revisions base 1, advanced 1, AVR 80 mega 644p 1. In summary, in this work, we presented 4 challenges for feature or feature revision location techniques to motivate the proposal of solutions for better mechanisms and tools to support the evolution of systems in space and time. We also made available a benchmark for comparing future work for supporting reproducibility. It contains a dataset and 2 utilities for computing metrics. And we also have our ground truth structure for new datasets available. Thank you for your attention. Any comments or questions, please do not hesitate to contact us.